All right, here we're getting into the connection between the Gibbs free energy, which is our new metric for judging whether or not a reaction is spontaneous. So we're going to calculate that first from tabulated Gibbs free energy as a formation, and then we connect it to K. So Gibbs free energy is delta G. And it's defined as the negative temperature times the entropy change of the universe for the process. So remember, this was where we originally landed. That's the second law of thermodynamics. If something is going to be spontaneous, this change needs to be positive. And then by definition, Gibbs free energy is that number times negative temperature, which means that if this is going to be spontaneous, if a process is going to proceed without intervention, then the Gibbs free energy should be negative. Okay, so that's what spontaneous means for us now. Okay, we didn't haven't gotten to this in class yet, but we are going to make a connection between the standard delta G of a reaction, which would be at the standard conditions. So when we have 1 molar or 1 atmosphere of our products, and we're going to connect that to the equilibrium constant for the process. Okay, so we will do that as delta G. And I'm going to make that standard of our process or of the reaction. So the Gibbs free energy change of our reaction equals negative RT ln of K, K being our equilibrium constant. Okay, so the process here is we'll calculate the Gibbs free energy of this reaction at standard conditions using these tabulated values. So let's start there. This number is equal to the sum of our Gibbs free energy for the products. And it's nice because all these state functions use the same, I don't know why I try and draw the dot first every time, but we always use the same structure. Sum the products and subtract the sum of the reactants. So our products are sodium hydroxide and carbon dioxide. So that's negative 394.3 plus a negative 379.5, and then minus a negative 851.8 for our sodium bicarb. And that got me 78 kilojoules per mole. Okay, so 78 kilojoules per mole is the answer here. And that tells me that at standard conditions, that we are not going to make more of our products. We're going to make more of our reactants. So I'm going to take the time to draw this out. Uh, for some of you, this probably doesn't land. I really like this visual, which is why I keep doing it. So here's if we had 100% NaHCO3, and here's 100% NaOH and CO2. Okay, at the middle, so where we have 50-50, or where K, like Q equals 1, that's standard conditions. These are standard conditions. Okay, that's how we define standard conditions, and we tabulate it there. Just because it makes things easy to always have to have Q equal 1. Okay, so we find at that point that we have a large positive number for delta G, okay, for our standard delta G, 78. That means that going forward, going this direction, because that's how we wrote it, going this direction is going to be an increase in Gibbs free energy. So that's non-spontaneous. So I should draw the hill like this. Okay, going this direction, going towards more of these would be non-spontaneous, which means that going this direction and making more of our sodium bicarb must be spontaneous. Okay, so the system, when it gets set up with standard conditions, we are going to roll backwards. And eventually we'll hit a minimum. And this is where delta G equals 0. and this is where K is. So K is going to be less than 1, okay? Because when we minimize our Gibbs free energy, we're going to have of our like more of our product, sorry, more of our reactants than of our products. Okay, so this is how we connect the two, sort of conceptually. Okay, so if we find ourselves with a positive value here, that means we aren't going to move forward. We have to move backwards, which means we're going to make less of our products and more of our reactants. Okay, we can make a quantitative connection between these 2 points. Okay, and that's what our equation does. So K, if I'm just going to rearrange the equation we had up here, connecting those two variables, K equals E to the negative delta G of the reaction divided by RT. Make sure that you use the right units. So I'm going to have E to the negative 78 kilojoules per mole. And then I'm going to divide by 0.008314 because that puts R into kilojoules per mole Kelvin, and then multiply by 298 Kelvin. Okay, so that's punch that in, and I already know I should have a small number for K because it's definitely less than 1, and we find that. We find that K equals 2.12 times 10 to the negative 14th. A really small number. Okay, so at standard conditions, which is this starting point here, more sodium bicarb will be made. Okay, that's what needs to happen. We're going to convert, and really ultimately, when you look at our, like just to bring this full circle, our equilibrium constant for this reaction is equal to CO2, the concentration, or I guess I could say the partial pressure of our carbon dioxide. And so we're going to have to decrease this pressure because it was 1 atmosphere, right, at standard conditions. And we know that this is our equilibrium constant. So I need to bring that 1 atmosphere all the way down to 2.12 times 10 to the negative 14th. And to do that, I need to consume CO2 and sodium hydroxide and make some more sodium bicarb.